All right. Yeah, well, thanks for introducing me, and thanks to the organizers. It's nice to get out of my mathy environment. Anyway, uh, basically, I'm okay. So the problem that damn it. Uh-huh. The problem that I'm somehow dealing with is this sort of paradox of intelligence, namely that if you go around asking people what does it mean to be intelligent or what intelligence is, they would somehow come to, I mean, if they ever manage to agree on something, they would typically agree on something on the lines of an ability to generalize across environments and to achieve goals. Anyway, this loosely translates to the notion of generalization, that you should be able to do well everywhere. But we know that this doesn't work well because to perform very well, you need to specialize. In machine learning or in computer science in general, we would explain this by invoking the no-free-lunch theorem. But if you're more into psychology, then you probably have seen at some point a comparative study where somebody finds out that in some very specific task, a pigeon is smarter than a human. So basically, I'll look at this, but not so much in the high level, like in high level cognition tasks, but rather in very simple tasks that are almost at the level of signal processing. I'll be using recurrent neural networks, and I'll somehow move a bit between machine learning and theoretical neuroscience. All right, so the framework that I'm going to be using is that of reservoir computing. It's a very simple idea. When you want to process a time series, you need some notion of memory. And to do that, you use recurrent neural networks. The problem is that training them is often very difficult. And the algorithm that we use for training neural networks, backpropagation through time, it can work, but it's not very efficient. So two labs came up with the idea at the same time of saying, well, if training recurrent neural networks is hard, let's just not do that. So what they did was to train only the last layer. In a way, what you have is a time series, then you send it to a large network of neurons that you can see as a large amount of filters that extract some features. And then you use a linear regression, which is something that's very easy to do, to map the features that these filters extract to the variable that you want to have. Now, if you go into this sort of literature, you'll find that they agree very much with the generalization idea, namely that there's many papers trying to find like the one reservoir that generalize well. And here I'm somehow taking the opposite approach and saying, well, how do I make sure that my reservoir is specialized to a particular problem? Now, since this is a machine learning problem so far, I'm going to use these three data sets. Mackie glass time series forecasting is a chaotic time series. It's just generated with your computer. Laser intensity time series forecasting, that's empirical, like it's real data, and it's considered a rather hard problem. And the third one is more classical machine learning, spoken digit recognition. Anyway, the main thing that I'm going to use is the fact that this reservoir is just a bunch of filters. And if I think of filters and I'm a signal processing person, then, well, the one thing you need to know when you do signal processing is that you have a signal with many, and you care about one particular frequency band, and that's what you're going to study. So if you're processing audio, for instance, you care about the frequency band that human speech is in. And that's the same thing here. So basically, I'm just going to narrow I'm just going to take my reservoir and make it enhance some frequencies and dampen some frequencies, but picking the frequencies that I care about. Okay, and the second thing that you need to know, I'll repeat that later, but it doesn't matter. It's just that to create filters, you can use feedback loops. All right. So before I jump into like the simulations and the results and what's not, I just want to give an intuition of how the math for this stuff works. I mean, nowadays there's a fair amount of works being done on the dimensions that the neural activity has, and this somehow goes in the same direction. Loosely speaking, what you do here is to say, well, when I'm training my reservoir, what I have, it's a large vector of outputs. I want an output time series. And in my computer, that looks like a vector. So that means that it's a point in a space. I have time 1, time 2, time 3, and each one of those is a dimension, and I put my output y here as a point. And now when I want to ask to combine my neurons linearly so that they approximate my point, so during training, what I do is I pick a linear combination of those neurons. That's a hyperplane or a linear subspace that passes through all the neurons. And in this space, I pick the point that is closest to my target. And the distance between those 2 points is the error in linear regression, which is the thing that you try to minimize. Now, if you try, what you would try to do in that case is to say, well, if I push my neurons towards my target, so if I push x1 up and x3 to the right, and x1 to the right and up, then I will probably do a better job because the distance would be reduced. And that's in a way what backpropagation through time tries to do. But it's very complicated because whenever I push neuron 1 up, I might be pushing neuron 2 to the left. So I can somehow I have to somehow be careful on how I balance this. So what I do is that say, well, I'm a signal processing person, so I'm just going to change, do a rotation. I'm going to change coordinates. And the only change of coordinates that I know how to do is a Fourier transform. Basically, it's just another coordinate axis where you look at frequency instead of time, but the distances are preserved. If you're a signal processing person, this is called Parseval's theorem, but if you're a physicist or a mathematician, you typically would notice that the Fourier base is orthonormal, so distances are preserved. Anyway, once you're in that newer space, the trick to play is to say, well, I just need my neurons to enhance the right frequency. So in that case, I know that y is very close to the axis f2. That means that I have to dampen frequency 1 and frequency 3 and enhance frequency 2. And there's a way to explain that in more mathematically rigorous setting, but I'm not sure anyone here is interested in that. So I'm just going to move to the second part, which is to say, well, how do I do this enhancement? And the answer is that you put cycles. A cycle in a network is a feedback loop, and a feedback loop makes things resonate. And basically, by having cycles of different lengths with different weights, you can enhance different frequencies. For instance, if you take your random vanilla state-of-the-art reservoir and you feed it with white Gaussian noise, with something that has all frequencies, it doesn't dampen or enhance any frequency, so it basically just keeps a flat frequency. But if you put cycles of length 1 with positive feedback, that's the green line with this variable rho that determines how many cycles you have of this length, then you enhance low frequencies. And if you put negative feedback loops, then you enhance high frequencies. And by having cycles of different lengths, you can enhance other families of cycles, of frequencies. Okay, that's not super important. It's just in case there's a mathematician in the audience, yes, this also works when the reservoir is nonlinear, as long as it's monotonic. All right, so now I'm just gonna put the things together, right? I have 3 time series of 3 tasks, and I just throw them at a reservoir. What you see here is basically in every column, you have a different task. On every row, you have cycles of different lengths. And in every subplot, you have on the y-axis the error, so lower, better. And on the x-axis, this variable rho, which tells me how much I deviate from the random network. So basically, if I have -1, I have many, many cycles with negative feedback for that particular length. If I have 0.5, I have some cycles of that particular length with positive signs. And the main lesson to take from here is that in some cases, you're okay if you're close to rho equals 0, which is the standard reservoir. But very often you actually need to get away from it. So for instance, in the laser intensity time series, you need negative feedback for cycles length 2 and 3. And for the spoken digital recognition, you need positive cycles. Now, you can also make an heuristic by looking at the frequencies and trying to match it with the cycles. And that gives you the black dotted line, which outperforms pretty much everything. But that's not this, that's useful if you're doing machine learning, but the point is just that by tuning cycles, you can specialize. So that's the short summary. Like you should whatever network you have should emphasize the tasks, the things that are relevant for your task, which is kind of trivial. In time series, this features that you should emphasize are probably frequency related. That's slightly less trivial. And finally, this frequency can be done by adding cycles into your network. Anyway, just a couple of things to be worried about is that the frequency enhancement works well with short cycles. When you have long cycles, it doesn't do much. It's a technical reason, but I'm not going to get into this now. And also the notion of frequency, I mean, the cycles are very useful in machine learning, but if you look at neuroscience, frequencies work slightly differently. Yeah, and in a way, that's what we're going to be looking at now. Namely, once you know that you have to somehow adapt your network to your particular frequencies, the next question is, well, how would you do that? Because we already said that your standard machine learning algorithm doesn't always work. And the main idea here would be to say, well, maybe I can do it with biological learning rules. And the general thought is this. Basically, if you have a neuron and it's connected to itself with a wire with delay 1 and a wire with delay 2, then the spike, if you make it fire every 2 seconds, the spike that goes to the wire with delay 2 with delay 1 would arrive when nothing is going out. So basically, this connection would not change if you know you're heavy on learning. Yeah, but if the spike that goes to the wire with delay 2 would be released and it would somehow come back to the neuron after 2 seconds, which is exactly when the next spike is going out. So you'll have something that emphasizes periods of 2, so you have your resonance and your feedback loop here. Now that's just the general thought, but being in a math institute, I had to make this thing way more complicated. And basically, I'm just gonna quickly go through the models. All the simulations that you're gonna see are done in a leak integrate and fire neuron. It's not the most advanced model, but it works for this. But the math is gonna be done based on rates. The general thought for this is that the neurons in most neurons in human brain have time scales that are very short, that are like 10 milliseconds, 20. But we live in a world that moves in seconds. And I have to and when you go from leak integrate and fire to something with short time scales to something in my time scales, then you can use the notion of rates, basically how much this neuron fires in a particular time window. And that gives you a rather standard model of this. Okay, then you go and say, well, what about learning? Well, I'm going to be using for the simulations of spike time dependent plasticity, the standard textbook neuroscience stuff. But to formulate it in terms of rates, I'm going to use some variant of Hebbian learning, which is called differential Hebbian learning. It's just a bit more general, but it's pretty much the same process. And on top of this, you have to put some notion of homeostasis, namely that neurons tend to change their excitability so that they keep a more or less healthy rate. So if you make a neuron, if a neuron is not firing for a long time, it's going to increase its firing rate by basically being more excitable and vice versa. You put those two together and you get this rather long equation that tells you nothing but to say that the change in weights depends on the homeostatic term and on the Hebbian or STDP-like term. Okay, so when we're in math, we can only solve very, very simple problems. So in that case, what I'm doing is to say, well, I cannot just throw these learning rules at any network with any input and hope that it will work. I'm just interested in showing that it can enhance some frequencies. So what I will do here is to say, well, I'm assume that I have a lot of neurons. And then I feed them all with a periodic input. And I'm using a periodic input because I'm interested in frequencies and only things with periodicity have some sort of frequency. And then I go and say, well, typically, if you do robotics or anything like that, you would have very few variables. Like, I mean, I'm not sure how it's for modern robotics nowadays, but 8 years ago, at least, when I worked in robotics, you would get 3 variables that describe what your robot is doing, or maybe 6 if you're interested in angles. And here that doesn't work. So you need to really have many, many variables. The way that I typically explain this by saying, when you're walking, is not that you have like 2 variables that describe how your legs are moving. You have a ton of sensors on your legs that tell you many, many things. And when you're walking, they give you very redundant information. which is perfectly fine. That's what your spinal cord and your lower motor areas work with. So that's basically what I'm reproducing here. I just have many sensors. They all send me information at different times, and they send something more or less similar to one another because they are neurons with similar properties. Okay, then because this system is so well behaved that basically all the neurons are more or less the same thing because they all get inputs from neurons that are similar, they just have a phase difference. You can just sit down with a piece of paper and write a bunch of equations and end up reducing that system to these two things. The shape is not particularly important. What matters is that you have basically one equation that tells you how the activity is going to be if you know the weights and the inputs. So that's fairly straightforward. Another equation that tells you how the weights are going to be if you know the activity. And after your system has learned everything, basically once it stops learning, you both have to be compatible. In the sense, for a given activity, you have a given weights, and for a given weight, you have a given activity. And that sort of self-consistency framework, then that's what somebody like me can sit down and study. And there's two solutions that come up fairly naturally. Like if somebody's interested in technical details, basically these two integrals here look like a convolution. Well, they are a convolution, and you can use this to basically find solutions of it. The first solution is, I mean, I didn't realize this until somebody pointed out that I was seeing grid cells, but loosely speaking, the weights look like a sinusoid, and if the input is sinusoid-ish and the weights are basically, then everything converges to a sinusoid. And yeah, basically it looks like a grid cell. Typically, you can enhance frequencies with this. In that particular plot, I wanted to show one funny thing that happened, which is that the activity after learning precedes a bit the activity before learning. So you have a notion of phase precession. And the reason I like this is because I did not really put that into the equations. It just came out of nowhere, and I was happily surprised by it. But basically, depending on your parameters, you would see the after learning curve to be much higher. It's just that then you cannot see the phase precession. Anyway, so basically, grid cells with this setting somehow emphasize frequencies. I mean, it's grid cells in time. It's not exactly the same thing, but it's close enough. And the second solution is something that people in robotics or neuromorphic robotics might recognize as a neural dynamic field. Loosely speaking, you have a line of neurons, and they only emphasize their neighbors and dampen everyone else so that they basically keep a peak of activity. If in that particular case, since I have like a asymmetric Hebbian somehow, like basically STDP, instead of being an activity that is maintained, is an activity that moves in a certain order. Yeah. Anyway, so basically the summary here is just that with STDP and homeostasis, you can get an analytical solution, and you get either grid cells or this neural dynamic field. Obviously, this all depends on what are the parameters of the STDP. If you pick the ones from B and POO, you get basically you get more or less the results that I showed you. But if you pick other parameters, then you get slightly different solutions on the same type of framework. Anyway, now if you ever want to somehow use this to have like a neuromorphic robot, and some of my colleagues here in ETH do, one has to be careful because most of the robots we typically work with have very few descriptive variables, because that's how classical control theories deal with them. But it's not necessarily how a very large network of neurons would deal with them. I mean, at least biological ones. Yeah, and basically that means that you need to have a bunch of sensors that are always active and always feeding a lot of high throughput data. Anyway, yeah, basically somehow the solution that I came to this paradox is that, somehow the tight way to wrap this up would be to say, well, you need to specialize to do well, but you can learn to specialize. And that somehow is like basically just a very general statement, but what I've been trying to do here is to do that in low level, almost signal processing problems. Now, the important lesson that I'm somehow trying to now bring somewhere else is that you can relate network structure to the dynamics that you have and these dynamics to the function that the network is supposed to do. In that particular case, it was done through resonances, but the same framework extends to a few other cases. Yeah, and basically biological learning rules can somehow guide where these relationships, what relationships can you look for? Because basically some things are incompatible with biological learning rules. And basically now I'm doing two things. First, I'm trying to use this with some group that do biologically inspired machine learning models by Johan Trisch. And the main bulk of the work is that we're looking at biological networks in low versus high cognitive areas. Loosely speaking, on the idea that the low cognitive areas would have a more specialized dynamic, so they would basically tune to fewer variables, while the high cognitive areas would need to have a higher dynamics, or basically a wide dynamic range to not necessarily do well in anything, but to basically be able to work across tasks. And that's done, that's basically a work that we're doing with Yang-Fang Peng from Charité. Well, now he's not, but with that, if anyone happens to want to read this, those are the preferences. And yeah, I have to acknowledge my collaborators, Yang-Fan and Gang, Tim Rogers and Hennig and Jürgen, and the ATH Fellowship Program, the Max Planck School of Cognition, and the Bundesministerium für Bildung und Forschung. That I think I'm 2 minutes over time, so sorry for that, and I'm happy to take questions.